Good. Okay, great. Hi, everybody. Thanks again for joining in for our Neurosymbolic talk as part of the Alan Turing Institute. It's our pleasure to have Leilani join us to give the talk today. As some of you might know, Leilani will be the program chair, or is it general chair from SC?
I don't know, but I think I'm doing.
Okay, one of the chair duties. Yeah, one of the chair duties for Neurosymbolic AI next year. She's currently at Santa Cruz, and previously she did a PhD with at MIT. Who was it with, Leilani? He doesn't say on your website.
Oh, with Jerry Sussman.
Okay, right. Great. Okay, fantastic. So great to have you here, and take it away. We'll do 45 minutes of slides if that's okay, and then keep around another 15 minutes for questions and stuff.
Perfect. Yeah, that works for me. Well, thank all of you guys for joining. I really appreciate it. I'm super excited to be here. So I'm going to talk about some of my work on neurosymbolic approaches for trustworthy, explainable complex systems. So my main area of research is actually in explainable AI, but a lot of the approaches I use to make them explainable actually have a neurosymbolic flavor. So I'll be talking about that a little bit today. I should also say, I'm happy to take questions throughout as well. I'll have a little bit of a sort of interaction part at the very beginning. So anyway, let's get to it. So let me sort of talk about the agenda. So I'm going to start by motivating the problem that complex systems fail in complex ways. And then I'll actually spend the majority of the talk talking about how do we build neurosymbolic approaches for autonomous vehicles. And in particular, I'll talk about different types of neurosymbolic monitoring architectures or local sanity checks that we can use alongside driving rules to make sure that cars adhere to the rules of the road and drive more robustly. Then I'll talk a little bit about how we're developing different tests for large language models. So I'll talk a little bit about how we've started to look at large language models, apply logical reasoning, and then basically create a neurosymbolic approach to making sure that large language models don't hallucinate for very specific types of questions. And then I'll kind of end talking about some ongoing work in explainable AI and neurosymbolic AI. And so the question that I'm going to be trying to answer in today's talk is, how do we develop neurosymbolic methods that can help us to anticipate and explain failures instead of doing an after-the-fact analysis? And again, this will all be in the context of complex systems, but I'll mostly be talking about self-driving cars. Great. So let's get to it. So let's start by motivating the problem. And this should be no surprise. I'm sure many of you have already seen this. So I'm going to talk a little bit about some of the failures that we've seen in autonomous vehicles. And what I'm going to start with is I'm going to start with this autonomous vehicle failure. And I'm going to ask you guys what you think happened here. What?
It just crashed.
Yeah, so it just went, this is in the second public trial. It goes completely to the right and crashes into the middle median. Can anyone think what could have been the reason for this failure? So they'd obviously tested it before it went on the track, but what could have gone wrong here?
Is it the curvature of the road?
Curvature of the road. Actually, it's related to that, but not exactly. Other ideas?
The track was different. The weather was different.
The track was different. Not exactly. I will, other ideas. I have yet for someone to get this actually in a talk yet. So it's
mechanical failure.
Mechanical failure. Actually, that's getting closer. Other ideas.
Blowout on the left-hand or right-hand tire.
Blowout on the right-hand tire. I'm trying to look at the chat. Some mud on the camera lens. Not exactly. The system detected something small and tried to avoid it. No. Okay. Any other last-minute ideas before I sort of throw out the answer?
Contrasted lighting.
Lactocausal, like.
Everyone stumped and then I say it and they go, oh my gosh, it's terrible. So this is actually a very interesting failure. So actually what happened, so some people mistook the wall for a road, no dividing line on the road. So it has nothing to do with the vision system. What had actually happened in this case was that somehow the steering and initialization was set to NaN or not a number. So there was some division by 0. And when that happens in this architecture, the default action was for it to go completely to the right. So related to what some people said, because they had a map of the road, the steering was initialized to go completely to the right, which is obviously the wrong thing that you want to do, right? But they had no way to check this. They, these sorts of constraints that they had, they don't have the types of neurosymbolic approaches we'll be talking about today, or the type of monitoring architectures to look and say, hey, I don't think that action is exactly right. So we'll be talking about how do we create these types of reasonable insanity checks to make sure these types of failures don't happen. And this is just one sort of example of complex systems failing in ways that a human never would. I'm going to show a bunch of cases from maybe everyone's favorite self-driving car, Tesla. So this is a Tesla that's from several years ago, where the car sees a bus side ad. Hopefully you can see my mouse. So there's a person on the back of the bus here. That's a person crossing the street. There have also been recent cases too, where here it is, sorry, let me go one back, where the Tesla thinks that this is a yellow light, right? But it's actually the moon. And more recently, what we've been seeing are these types of adversarial attacks where they'll put just a few pieces of tape on a stop sign. And even though we can look at that and clearly think that that's a stop sign, at least a US version of a stop sign, with just a few pieces of tape, the self-driving car vision system now thinks that this is a 45-mile-per-hour sign. And obviously you can see the types of ramifications that would not only have for the vehicle that you're in, but also for all the cars around it. I want to bring up one more point here, which is issues of bias. So as many of you are probably aware, computer vision systems are generally better at detecting faces with lighter skin tones than darker skin tones. And in this paper by Wilson et al., what they showed was that all of a sudden, if you put the same technology on a self-driving car, all of a sudden the self-driving car is better at predicting pedestrians with lighter skin tones than darker skin tones. So there's a lot of issues that can come from these types of technologies. And yeah, lot of interesting self-driving car failures. I just saw one in the chat, so we can definitely talk about all those. I'm always looking for new and great examples. So if we kind of look at where autonomous vehicles are now, and I know they're a little bit different in in the UK than they are in the US, but really we have autonomous vehicles at two extremes. We either have cars that are very cautious and not comfortable. This is what happened in a General Motors ultra cautious self-driving car. So this is what happened when the car would start and stop for anything in its way, regardless of whether that was a pedestrian or even a plastic bag. Now, what are the issues with that? The issues are that the person in the vehicle kept going sort of back and forth with the starting and the stopping of the car, and it actually gave them sort of a false sense that the car was very unsure, even though it was adhering to these types of safety constraints. So we have to be very careful that we're kind of between the comfort level, making sure that it's not comfortable for people, but we have to make sure that they adhere to these strict safety standards. On the other side, what I'll be talking about and what a lot of the examples that I've been working on are on the first Uber pedestrian fatality, which occurred in 2018, which is where the Uber self-driving car wasn't sure of what it was perceiving. And so unfortunately, it struck and killed a pedestrian crossing the street in Mesa, Arizona. And the reason that happened was because they added confidence intervals. So they said, now we're not going to start and stop for anything in our way. Now we're only going to start and stop if we're very confident of what we are perceiving. And so what I argue is that what we really need is we need better reasoning, right? We as human drivers aren't trying to do belief propagation and figure out what the probability that this is a person crossing the street versus a plastic bag. What we're doing is thinking about that symbolically. This is something moving and it's something we should stop for. And that type of common sense and reasoning is exactly the types of approaches we're going to be talking about today. And this is also very inspired by the way that human organizations work. I'll just sort of briefly go through these types of diagrams, and then I'll talk about the technical contributions of it in a few slides. So, you can think about a human organization, at least very high functioning ones with sort of hierarchical structure, as having a bunch of groups that are working on the same task. You have a set of managers one level up, and then maybe another set of managers above that, so on and so forth. And what you can think about this as having hierarchies of overlapping committees. For example, on a software engineering team, you might have a group of software engineers, you might also have a group of test engineers, and then you have a couple people in the middle who work on both. But to be able to be effective, you really have to facilitate this type of continuous interaction and communication. And this is actually what's done with our local sanity checks, which I'll talk about today, which are ways that you basically monitor an opaque system for making reasonable decisions. And then if a failure is made, then we can create a story that combines those members' observations. And that's actually what we use with an explanation synthesizer. I won't have much time to talk about this today, but happy to send some resources if that's interesting. And basically what that does is that reconciles conflicting reasons if the different parts of a complex system are unsure of what they're perceiving. The nice part about this is this can actually mitigate the types of common problems that we see in self-driving cars. So the local sanity checks can handle the cases of the trollable self-driving car. What does that mean? It's talking about the long tail of errors that we see in self-driving vehicles. We're able to justify new examples even if we haven't seen them before. And then if we look at what's happening with some of the deadly crashes that we see now with Uber and with Waymo and other things, this is able to reconcile conflicting reasons. So if the vision system is unsure of what it's perceiving and the LiDAR system is sure of what it's perceiving, how do we basically reconcile those conflicting reasons? And that can also be extended to thinking about how does this work when you have an autonomous vehicle that's conflicting with a human, right? A human is just part of the complex system. So we'll talk a little bit about driving rules to handle the local sanity checks, and we'll talk a little bit about explanations to help reconcile these types of conflicting reasons. But let's actually show how this actually works. So what I'm going to do is I'm going to actually show the Uber self-driving car accident. So just trigger warning, you will see moments before the accident occurs, but not the actual accident. Again, this was recorded in Mesa, Arizona in the United States in 2018, and the first reported pedestrian fatality. So what you'll see going on here is the car is going very quickly. So apologies, I'm going to say it in US metrics. It's going about 47 miles per hour. You'll see it's traveling at night. There's a bunch of shrubbery on the side of the road. And what happened was that the computer vision system was unsure of what it was perceiving. And in fact, the vision system of the car was kind of the single modality that they were looking at. This is also a problem we see with Teslas where it's not taking into account sensors. So even though the LiDAR unit had detected the vehicle with enough time to stop, it didn't know how to deal with those types of conflicting reasons. And so this is actually the example that I ended up using in my PhD thesis, which is now 4 years ago, but just to kind of show, this is kind of the starting branch of what we work on in my lab. So basically you monitor all the different parts of a self-driving car. Obviously, there are more components than just the vision, the LiDAR, and the tactics, but for simplification. And this also occurred before ChatGPT. So all the explanations I'm going to be showing today are generated via templates, not via generative AI tool. And so what we find is that if we use reasonableness monitoring, which I'll talk about today, and if we use explanation synthesizer, then what we find is that the best option for the vehicle was to veer and slow down. And this is in our simulations after the fact of the accident. That the vehicle traveling too fast to suddenly stop, that the vision system is inconsistent, but the LiDAR system has provided a reasonable and a strong claim to avoid the object moving across the street. And we can kind of highlight those parts of the actual explanation to show what was important according to the LiDAR, the vision, and the tactics. And so what I'm going to be talking about today is exactly how we generate those types of explanations. So I'll be talking about the types of checks and the driving rules that we do to do that. Any questions so far? Maybe I can take a quick question before I move forward.
Hi, Leilani, just wondering what you mean by sanity checks. Is this something that's codified, or is this informal based on the domain?
Yeah. So it is codified. I'll talk about how we generate those, but they are also domain specific. So, you know, a sanity check for a self-driving car is going to be very different than the sanity check that we show for the large language models. One quick thing in the chat. Would a human have managed to avoid the cyclist? That's a very good question. We actually haven't done those types of experiments. But again, what we do know from the autonomous vehicle is that the LiDAR had detected the person with enough time to stop. So an autonomous vehicle could have, if it was using that information. which is what we showed in simulation. But I don't know about the human analog. I don't know if they've actually done those experiments. Okay, so let me just sort of move on. Let me talk about how we're going to develop these types of sanity checks for self-driving cars. And what I'm going to start with is kind of a theory of how do we think about complex system failures. The failure can either be local to a specific subsystem, or it can be due to a failed cooperation amongst subsystems. So I'm going to specifically talk about the failure that's local to a specific subsystem, and I'm going to specifically talk about two different technologies in a self-driving car that we might want to look for local failures. And in particular, I'm going to talk about that for the camera data. Now, I'm going to do computer vision 101. So, how do we process camera data in a self-driving car? Well, a neural network will label your camera data for you. So you'll get some input image. Maybe you have a frame of reference that you're particularly interested in, like this pedestrian here. You put it through some deep neural network, some convolutional network, like the Inception network from Google. And what you get is a label. For example, this is a pedestrian. Now, this works great most of the time. And for those of you that work on computer vision, we really surpassed human accuracy on a bunch of tasks, but these networks are brittle, right? So best example are the types of adversarial examples that we see, classical example. So, with just a little bit of noise, this picture of a pig, and we just add, a little noise here, obviously, and hopefully everybody here says, yes, that is in fact still an image of a pig. All of a sudden, the deep neural network thinks that this is an airliner. We already saw an example of what this looks like in the self-driving car literature. You can also do this in physical attacks, right, with a few pieces of tape. They think that this is a 45-mile-per-hour sign. And what I'm trying to allude to here is, yes, these are, very small probabilistic cases. They don't happen a lot in the wild, but in the cases where they do happen, they have huge impact. And so when we're looking at self-driving cars and other mission-critical, safety-critical applications, right, these mistakes have consequences. And so we really need to develop approaches to monitor these systems and to figure out what they're doing right and what they're doing wrong. So what our solution has been is to monitor these opaque systems for reasonable behavior. So, it's very difficult to actually explain the internals of a deep neural network. We do have some work in my lab about that. But for this particular application, what we do is we treat the underlying model as something opaque. And we just look at the output label. Now, this is important for a couple different reasons. One is that, especially in autonomous driving, this might be opaque by design, right? You have a self-driving car or you're using it, that algorithm is proprietary. You wouldn't get access to the model even if you tried. And the other one are that they're so complex that they're opaque. So there are really two cases where we wouldn't even be able to peer in, even if we had the ability. And so what we're just trying to do is take the outputs that we see here and monitor whether they're reasonable or not, given the domain. And so we do that by having a common sense knowledge base, a flexible representation, having some rules to identify what is unreasonable or not, and then developing an explanation or a justification of why. And so this is all leading to a justification of whether the label, for example, here, this pedestrian, is reasonable, and a justification of why it is reasonable, which is, again, very important in the case of an accident or failure. And so the system that we built to do this, which we call reasonableness monitors, basically has all those parts. So it takes in the output of some type of opaque mechanism, represents it flexibly, has a set of rules, supplements that with common sense knowledge, and then develops an explanation of why that's reasonable or not. Now, for today, I'm just going to kind of focus on the representation, the sort of neurosymbolic side, so that I can talk about the types of rules that we've developed to make this actually a reality. And so what we have to do here is we basically have to take a bunch of signals and we have to represent that in some type of symbolic form. And the symbolic form that we use is a primitive representation. And I don't know if anybody here is familiar, but we actually use conceptual dependency theory from Schenck in 1975. And I know that that sounds like something super, super outdated, but actually this ends up working fairly well because what Schenck was able to do is he came up with a representation to account for most actions. And we looked very closely at the 5 for physical action. So that's ingest, expel, grasp, move, and propel. And of course, a lot of those are not very applicable to the autonomous driving literature. So we also extended that to different specific vehicle primitives that you would want, which is much motivated by the robotics literature. So for example, turning left, turning right, yielding, etc. So we have that representation of sort of the primitive movements that an autonomous vehicle would do. Now, the big part of this, which makes it difficult, is to actually parse this type of natural language into the representation that we would want. Again, what we're relying on is we're relying on some type of image, and we need to now turn that into this primitive representation that we can use to trigger different rules. So I'm showing data from new scenes. This is a self-driving car data set, sort of state of the art. And let's just say that we've identified this as a woman, and we're able to, by putting this through one of the visual captioning tools, we're able to get a description of what that looks like, a woman crossing the street. Of course, you could also throw this into your favorite generative AI as well. And basically what we do is we take that, we build our own custom natural language parser, and then we bind the subject, the verb, and the object to the specific parts that we're interested in. And we do that via a common sense knowledge base. So why is that important? Because we don't care that this is a woman crossing the street. All that we care about is that this is a person and they're moving in the direction of the street. And that lets us actually encapsulate the reasonableness of particular scenes in just a few small rules. And so if you're actually to represent this in the sort of representation that we're talking about, this ends up looking like this. You don't have to worry too much about that. Let me just see, I saw some stuff in the chat, oh, I'm good. Oh, so yes, I'll get to the common sense knowledge base that we look at. And then I'll talk a little bit about how we actually do this for prediction as well. Okay, so let me kind of get to the neurosymbolic angle and what people might be interested in. So one of the wonderful things with this type of representation, for those of you that are familiar, the one person that is that this representation actually has implicit rules built in. So for example, if I say that I'm looking at a person moving in the direction of the street, then I know that moving is reasonable if, right, the actor, so who's ever doing the movement towards some location, okay, I'm calling the actor X, I'm calling the location here Y, right? And that will be if X has the property that it's adamant, so the actor can actually move, right? And the actor is located near where the street is, right? And so what's really nice about this type of representation is we have each one of the primitives have a different reasonableness rule. And again, we'll have multiple types of primitives that are representing our scene. Of course, when we're looking at a self-driving car, we're not just looking at one person moving. There can be several different people moving. There can be several different cars doing different actions. And for a particular snapshot that we're looking at, we can say that that perceived frame will be reasonable if all of the primitives we have in that frame are reasonable. So it ends up actually working pretty well. And again, because we're binding this to sort of higher level representations, we don't end up having sort of the huge rule blowup that you would have in typical symbolic systems. So let's actually talk about how we do this monitoring in real time and on real data. So again, I'm talking about this in new scenes. So one of the things that I won't talk about today, but just to give you guys some idea, is again, this data is basically represented as an image and a bunch of auxiliary data that we have about, where they are, the size, the rotation, the location. We take, again, we use a neural processing system to take care of that and to build our representation. But now, how do we figure out what types of concepts we actually bind this to? And there was a question in the chat about what type of common sense we use. We end up using ConceptNet. And some people might be excited about ConceptNet, but there are a lot of issues with it. So one thing is that, if you look at the true definition that we have of this in new scenes, it doesn't say that it's a woman, right? It says it's a human pedestrian adult. And so what we want to do is we want to find, okay, what are the specific properties that this adult is capable of? If you look that up in ConceptNet directly, you're not going to find anything useful, right? What you're going to find is, adults are capable of helping a child, dressing themselves, drinking beer, things that aren't really applicable to the type of thing we're looking at. However, there are certain hierarchical knowledge, for example, what an adult is a type of, it's a type of, type of person, type of animal that has certain properties like they're adamant. And those are things that we're going to want to use. And so what we end up doing is we end up filtering our common sense knowledge base to get the type of information that we really care about. And so the first thing we do is we basically filter that on the specific types of relations that we care about, which is a domain specific list. And I can go into that in more detail if people are interested. But the big takeaway is we don't use the whole common sense knowledge base. We filter that for the particular relations we're interested in. And so when we actually do this in real time, basically what we do is we pass this into the monitor frame by frame as the vehicle's driving. And basically what we'll say here is, okay, in the case that we have this image, that this is a human pedestrian adult, we say that this is reasonable and we can develop a reason why. And so what our monitor tells us is that this is reasonable because it's an adult, it's typically a large person. They're usually located walking on the street, and their dimensions, which again, that's information that we got from the data itself, is approximately the correct size in meters. So fantastic. The big problem that we ran into with this system, right, is that this is actually used for error detection, right? But we don't have any errors in the types of autonomous vehicle data sets that we're looking at. And so what we ended up doing is we ended up building an unreasonable image data set just for our own testing. And we're actually extending this work today. We're trying to develop a photorealistic data set of autonomous vehicle errors. And I can, again, talk about that a little bit more. But at the time, basically, we did this for 100 different descriptions with different words, verbs, nouns, etc. And we also looked at self-driving image processing errors. So we also did a real-time evaluation with a vehicle simulator that's called Carla. We added errors on existing autonomous vehicle data sets. I'll show what that looks like. And then we also looked at some of the errors that people had on the autonomous vehicle challenges as well. But again, our current work is on building these challenge problems and scenarios, which is a very difficult thing to make it actually photorealistic. So let's actually show what an error would look like. So what do we talk about when an error occurs here? I mean, let's say that this is the wrong object. It says this is a traffic cone. Okay. And this actually happens, is that some of the labels in the real world, it will, you do a lot of CAPTCHAs, I'm sure, where you have to say if it's a taxi car or if it's a skateboard. And so these can easily get mislabeled. And so in this case, this is a very simple example, but it finds that it's unreasonable because it's too tall and there's no common sense supporting this judgment. And so it ends up basically discounting objects that are located in the region. And again, because we're only looking at a few small rules here, we can actually do this type of inference in real time. Cool. Maybe I will pause in case there are questions before I move on to how do we actually represent the rules and what do they look like?
There seems to be one or two mentions in the chat, Leilani.
Okay.
But you could also do questions at the end.
Yeah.
That's fine.
Are there errors associated with temporary occlusions? Not in the autonomous driving data sets we've looked at. So unfortunately, one of the major problems that we see are that these self-driving data sets are perfectly curated, right? Because they're used for these challenges. So you really have to add those. And again, that's a lot of what the work in my lab is on, is we will try and basically create more realistic data sets by adding different types of noise and occlusion and other things. Let me maybe move on just so I can get to the rule portion here and make sure we have enough time. So the work that I'm going to be talking about today is part of a much bigger effort to create robust autonomous vehicles that are safe, secure, and explainable. This is with myself and several other faculty at UC Santa Cruz. We're part of a Department of Transportation grant where we're working on security, verification, and adversarial machine learning. But what I'm going to talk about a little bit more is the specific specifications that we use for driving rules. So far I talked about kind of the rules that we would have for low-level vision, but again, there are many layers of the autonomous driving system that we have to monitor for. And one of the specific things is making sure that cars drive safely. And so what one of our vision is to create actual driving tests for autonomous vehicles. I don't know how it is in the UK. I assume it's similar to the US. But when we as humans want to drive, we have to go in, we have to take a dynamic driving test in a dynamic scenario. Someone evaluates us and says whether we're a good driver, whether we adhered to some rules of the road. And you're supposed to memorize those rules and apply them in a real world scenario. currently for autonomous vehicles, at least in the United States, and especially in California, the way that they're evaluated as good drivers is basically if the mayor signs off a sheet. And so what we're hoping to do, and I'll talk about some preliminary work here, is to dynamically generate these driving test scenarios in different environments using the specification of the driving rules that we've created. And so we actually have a project on exactly that. So taking driving handbooks, which you'll get at the Department of Motor Vehicles in the United States, and basically codifying them in a formal logic so that you can actually apply first order logic, backwards chaining, and other things, and actually validate whether the car is adhering to the rules of the road or not. Right now, this is a semi-automated process, but we're working on making it fully automatic in future work. So let me actually show you guys what that looks like. So in our first iteration of the system, we actually represented this in AMORD and RDF. So this is a sort of RDF variant framework of rules. And what's really nice about it is that you can actually put in descriptions so that you can get explanations of what happened when the specific rule was triggered. And what's also nice about this is because this is in a reusable web format, one, you can combine it with a production level reasoner, which is really nice. But the other thing that you can do is you can imagine that you could share rules across vehicles in vehicle to vehicle communication. Of course, some of these rules might be different for different cars, right? So another thing that we're also looking at are actually analyzing these rules and seeing whether they make sense for the applications that we're looking at. So, one example I always give is I'm from California. I don't know how many people are familiar with the States. I won't give the US UK example because I can't drive on the opposite side of the road. But when I moved to Boston, Massachusetts for my PhD, the sort of rules of the road that you would see in Massachusetts are very different than you would see in California, right? And it would have been great if you have that same process for an autonomous vehicle, you just transfer a new state's rules to another thing. So let me show some cases of what this actually looks like. And again, we represent this in a sort of symbolic triple language, but you could do this in a lot of different ways as well. So the types of rules that we can actually learn from these handbooks are also some common sense issues that maybe you hadn't thought about. So for example, if self, that's your vehicle, right? If you're encountering a dust storm, then you want to reduce your speed. So you could imagine this could be synthesized with multiple pieces of information where autonomous vehicles can get weather reports and then correlate that to the camera feed and adapt their driving behavior. Another thing that you might see, this is very common in a road right by my house, is that if you have a trailer, then that can cause a jackknife. So a jackknife is basically where the trailer is kind of sitting here on one side here. And this is important because, a lot of people don't know how to drive around these types of one-off scenarios. So autonomous vehicles here can attempt to identify if they're pulling a trailer or not, so that they can drive accordingly. And so these are the types of rules that we're developing. Of course, these are manually validated right now. And our current work is basically to do automatic extraction. Okay. So that was all that I wanted to talk about in autonomous driving. But now what I'm going to talk about is a little bit of tests for large language models. So let me talk a little bit about that. I'm just going to check the chat really quickly. Maybe I'll handle this after. Yes, I will share the link after. And I'll come back to the questions a little bit later so we can get through this part. So I'm going to talk about how we take a similar type of approach, but we do that for large language models. I'm sure most of you guys are already familiar with the problems with large language models. They're opaque and they produce false information. So they hallucinate. Their reasoning process is not transparent. You could say they're explainable because they will explain their reasoning, but I'll talk about why that's not very good. But they're not interpretable, and it's not really traceable what they're doing. Of course, there are some techniques that are getting closer to that, but as a whole, as a class of algorithms, we're not there yet. There are some previous solutions, so chain of thought, retrieval augmentation, and one of the biggest ones is post hoc explainability. And in our work, that's actually something we've looked at is, are these large language models able to actually explain themselves? You can ask it why it came to the judgment it did. So if you ask it, should I go to the store today? You can ask it to explain its reasoning. But they're not very good. So what we did in our initial work here is we examined some of these large language model self-explanations on movie reviews. So on, is this movie review positive or is this movie review negative? And what we actually did is we examined the feature attribution, so the word score. So we also asked the large language model to generate its word confidence related with its description. And we looked at validating the explanations with typical explainable AI metrics you would see: comprehensiveness, efficiency, rank correlation, etc. And you don't necessarily need to know what those means, but the takeaway is very important. What we found is that those explanations that the LLM generates, they are not faithful. They don't actually support the judgment of the model. So for example, if you say that this is a positive movie review because, you know, I loved it, it was the world's greatest film, X, Y, and Z, it actually doesn't highlight the key words that were important to saying that this is positive. The explanation it actually produces, what we hypothesize, is something that the users want to hear. So we can't really trust these types of explanations. And so what we've instead done is we've been thinking about sort of refining LLMs. So maintaining a domain-specific knowledge base with rules and augment that through experience and expertise, including different time series, time-sensitive information. And let me kind of give an example of what that looks like. So, you know, the running example that we're using in this work is how many dining halls there are at UC Santa Cruz. And you guys don't know that, but we know the answer here at Santa Cruz, right? And if you ask ChatGPT, this was a few months ago. So one of the problems with this project is that, you know, they're always making these LLMs better. But it used to say Santa Cruz has 3 dining halls. These dining halls are located at different residential colleges on campus and offer a variety of meal options to students. It would also list those dining halls, so it would tell you what those are. And, you know, each dining hall serves students. Great. But you don't actually have to know anything about UC Santa Cruz to know that this seems a little bit wrong. Santa Cruz has over 19,000 undergraduates. I have a tough time believing they only have 3 dining halls on campus. So, you know, we know that this is clearly wrong. Now, how do we develop sanity checks, the same ones that we developed for self-driving cars, to monitor these types of systems? And so, you know, essentially what we said is, well, we can do very similar to what retrieval augmented generation does. We can just read from the website, right? If we look at dining.ucsc.edu, we find that there are actually 5 dining halls. And what we can do is we can actually ask the large language model to generate this in a logical language for us. And shockingly, we use Prolog. And so the sort of big takeaway from this project that we ended up doing was that these large language models can actually generate Prolog, and then we can use this Prolog to do inference and then generate the Prolog back to natural language to provide a better explanation to the user that we feel has been verified. And again, it works. It actually ends up working pretty well. So let's actually talk about, you know, how we built this into a production level system. So again, we're going to be using first order logic and chain of thought for the LLM to reason, inform, and answer. So we have facts or contextual factors. Then we develop the reasoning for all of the said facts. And then the reasoning over these facts form a final answer. And so what that looks like as a sort of full system diagram is the user inputs some type of question. Right? We take that question, we translate it to Prolog into a Prolog query. Okay. This then goes to the symbolic component where we basically compare that against the knowledge base of information. Okay. And then we evaluate the truth value of each query. And then the user output, basically we generate a sort of interact layer on top of the large language model and actually show the user that actually, you know, this is false. And we have another explanation that we think is better. And this system can be used for a couple different areas. So far, we've only looked at this for fact checking. So for doing hallucination detection and explanation. For example, the answer you get from the LLM here is clearly wrong. This is the answer that we can validate is right. And we do that by backwards chaining to the goal query. This could also be used for, of course, user personalization, which is what a lot of large language models use for retrieval augmented generation. But we haven't done so much work in that yet. The sort of big idea with this is that this backwards chaining can build a proof and therefore trust. So, I mean, I'm sure I don't have to explain to this audience. So the idea of backwards chaining is basically you start from the goal and then you sort of chain your way up. So, you know, examples, you can say, where are my keys? How do I get to my next class? And the complexity in backwards chaining, which makes this actually quickly, is that it can be much less than linear in the size of the knowledge base. And what we're really excited about is that this actually creates a goal tree or a proof, and that is interpretable and understandable. And so you can actually see the way that we've done this as a schematic. I'll sort of walk through this. So again, very similar to what we saw before. There is a generation of prologue, backwards chaining, and then that's basically thrown back into the interface and shown to a user. And we also have a similar user personalization workflow where we also get the user's knowledge base as well. So, the current application domain that we've looked at are these UCSC specific queries. So, where students will immediately know the right answer, and the web information is available but consistently wrong. So one of the other applications that we're working on are things like where there are openings on campus. So maybe you guys have the same problem. So I'm a big avid swimmer. If we look at the UCSC website for the pool, it even says, hey, the app is not correct. Right. So the idea is that it can also sort of validate time-dependent information as well. It can automatically retrieve and say, has this been changed? Should we change our knowledge base? Other domains that we're thinking about for future work are individual biographies. So one of the places where a lot of these large language models fail are, again, if you ask them about individuals that are not well represented. For example, one of my favorite examples is if you look at my advisor, Jerry Sussman, it says that he founded the AI lab at MIT, which is clearly not true. Actually, his advisor, Marvin Minsky, founded the AI lab at MIT. But again, with a knowledge base of information, we can validate that against each other. The other thing that we're really interested in is also looking at medical case studies. So case studies where you might not know if the right information is correct. Let me just kind of show quickly what that looks like. So again, this is a very simple example of what we'll see. So you might want to know a quiet place to study on campus. And basically what we get is, for my student Priyesh, if Priyesh says, I want to know a quiet place to study, it basically finds the place that you should study for the particular student. And so you get this in terms of your symbolic component, and the goal tree provides this type of explanation for you. And then we can take that goal tree and also express that in natural language that can be shown to the user. So taking the prologue context to natural language, saying, hey, the place must be quiet and the place must have Wi-Fi. So you have to have both of these preferences. And again, this can be determined by the user, or we can use existing knowledge that we have. So again, it can be used for user personalization. It can also be used for a more general use case. This work is still pretty preliminary. We're actually trying to get to a place where we can deploy the system. We're still working on what happens if the facts that we need, the information, is not actually in the knowledge base. And the big thing that we're currently exploring is, can we use a large language model to help us update and write new rules? So I actually have a master's student that's working on that right now. Great. So I've talked about, a couple different applications now. So I talked about autonomous vehicles, I talked about large language models. And so what I want to do in kind of the last, minute or so is I want to talk about the sort of ongoing work, or sort of the future direction of explainable AI and working on neurosymbolic. And so, if we think about kind of where we started this talk, I talked about this fact that systems lack common sense. And a lot of people also brought up, well, what would humans do in that situation as well? But a lot of what we see is that these systems, they fail in ways that a human never would, right? And what I've said is a possible solution is an explanation. And I've done a lot of work on explanations, thinking about what makes a good explanation, how do we evaluate it? But no one's really thinking about dynamic explanations in uncertain conditions in the real world. And no one's really thinking about self-explaining architectures. And so what a lot of I've shown today are architectures that are neurosymbolic, but they're also self-explaining. Because we have that symbolic component, there's actually an explanation built in. And so, what my sort of long-term vision is actually to facilitate this type of coherent communication in a common symbolic language with other systems, but also with humans. So, we can think about a learning system passing to a symbolic system, which is a lot of what I showed today. But one of the things that we're working on are ways that these can actually communicate together in a common language to complete tasks. This is important for redundancy, so that systems solve problems in multiple ways, but also for hybrid processes, the systems that learn from each other. It's also important for humans to interact with complex systems. One of the things we haven't talked about is really the humanistic aspect here, with explanations really being this debugging language, so that humans can improve complex systems, but also for education, so that complex systems can, improve or teach humans. And actually, I think that we're very close to a lot of these things. I always show my students in my AI class the sort of hype cycle for artificial intelligence and kind of where we are. And you can see a lot of the hype right now is really on generative AI. But I think that a lot of what we want to look at is the kind of neurosymbolic AI, which says it's in more than 10 years. But I think we have a lot of the tools. For example, if we go back to one of the examples I showed earlier, right, with the Tesla thinking that the moon here is a yellow light, we have a lot of that information, right? Actually, a lot of the information we have from common sense knowledge bases says things like, actually, the location of a traffic light is at the corner of two streets. We could validate this information very quickly. We just need to build mechanisms that can do it. And this has impact, across different systems. So for society, so that you can articulately communicate with humans on shared tasks. For liability, I haven't talked about, but the fact that systems can testify, answer questions, and provide insights, but also for robustness, so you can do dynamic detection of failure with precise mitigation. And all of these are sort of implications of having these types of systems and building the safety culture around autonomous systems. So let me kind of just summarize what I talked about today, and then I'll be happy to take questions. So, I started by motivating the problem. I then talked about local sanity checks and driving rules. Then I talked about tests for large language models. And I sort of ended here with talking about some ongoing work in explainable AI and neurosymbolic AI. And again, what the goal of this work really is to, make sure that autonomous vehicles are able to handle these types of situations, which hopefully you guys don't see every day, but I do driving around campus. So anyway, I will stop there, and I'm happy to take questions. I saw a bunch on the chat, and I thank you all for your attention.
Thanks, Leilani. Really wonderful. I think you really covered a wide base. Before you get into the questions, I had just one or two thoughts, and I wondered what your views on that were. The first thing was, it seems, I think you make a case quite nicely. Maybe the last bit of work really touches on this, that in some sense, logic is providing the guardrails for some of the predictions from these systems. But this, of course, has this problem that maybe a lot of the predictions are essentially incorrect. And of course, in the end, you could pass these predictions to the gatekeeper and discard a lot of them. But what can we do to make sure that the predictions are mostly in line with the constraints? As you know, there's an area of research on loss functions which tries to do this, but in that area we have other issues such as scalability. I wondered if you had some thoughts on that.
Oh wow, what a great question. We haven't looked at that question directly, just because a lot of the applications that we're looking at, kind of just like what I said, like a lot of them are proprietary algorithms. So we just have to sit and hope and pray that the predictions are fairly correct. And a lot of what happens, especially in autonomous driving, is they'll tell us, like, our accuracy metrics are this. We just want to catch the last tail 5% of errors. But I think there is a lot of work to be done in areas like, for example, for an LLMs, like fine tuning, which we've seen is actually done remarkably. Actually, I have a whole nother area of work I didn't talk about today on looking at instructing LLMs when they don't know information, and we did all of that with fine tuning. So giving it a data set of unknown information and seeing how it does. So I think there's a lot of really interesting work on that area. And I have a lot of thoughts, but unfortunately, the types of systems we've looked at, that's not been a possibility for us to think about. So,
do you think it's ever possible that at some point, if the LLM is trained on sufficiently many patterns of logical steps, it could mimic the function?
Oh, that's interesting. That's interesting. I don't know. I think that the people working on chain of thought would say yes, but I think that they, even with GPT-4o, they're still pretty bad at reasoning tasks. And
Yeah.
I think actually even beyond that, they're still pretty bad at counting.
Yeah.
So, and I don't know what the solution to that is. I think if you were a machine learning person, you would say the answer is more data. And I think if you were a symbolic person, you would say that they'll never have that ability. But I think it's somewhere in between, right? Like, again, I think that having these types of sanity checks are essential. We have them for any safety critical system, right?
Yeah.
But we actually need to work on incorporating that into feedback. And I think that's an interesting area that I haven't explored yet. So.
Good. So there's a question from Alex and a bunch of questions on chat. Just a note, when you answer the questions from the chat, if you could summarize or read the question, just so that when we upload on YouTube, people know what you're talking about. But anyway, Alex, I think, raised her hand.
Thanks, Vaishak. Thanks for a really stimulating talk. So my question is about the defeasibility of common sense symbolic information. So you're using rules to do these sanity checks. And one of the rules you mentioned in passing that you'd use to, predict that the moon is not a traffic light is that the traffic lights are on the corner of roads, but there are unbounded exceptions to that. And so there are logics that can account for exceptions to rules that do defeasible reasoning and allow a system to be consistent even when a given fact violates a default rule, which that traffic light location thing would have to be, right? The common sense thing. But then you have a problem because you then got to assess whether it's an exception to the default rule or whether the default rule is the reason why the prediction is unreasonable. How would you cope with that?
Oh gosh, I mean, that was a big question that I actually ended up in my thesis. So, and that I didn't solve. So I guess maybe there are some grad students here that this is a wonderful problem that somebody should work on. But let me kind of describe what we saw happen. So we had this interesting idea that you could kind of learn rules from explanation, which is that, a huge area that people have worked in robotics. But, the idea is that, as we're driving as people, if we see a new circumstance, we usually create a new rule. So an example I give is that the first time I was driving in a very narrow parking lot, someone flashed their high beams at me. Now, usually in the US, someone flashing high beams, that means to turn on your lights. But in that instance, because it was well lit during the day, that was a warning signal. So I learned that from experience, from my explanation, right? That, okay, well, I'm in this context where I don't have to turn on my lights, but this car is going very quickly. Okay, this is a warning symbol. And so we kind of took this idea. So if you can constantly explain what you're doing, can you learn new rules? And I think this should be no surprise to the symbolic people in the audience or anyone who works on this. What happened? We ended up getting thousands of rules, way too many rules. Huge rule blow up problem that we're all used to in the field. And I remember explaining it to my advisor, and he said, "Oh, well, you just encountered the biggest problem in symbolic AI. You're not going to solve that. What you're going to do is you're going to filter these down for the time being, and then have another student handle that." So, I mean, I think that this is actually related to a lot of the problems that people are seeing in the long tail of autonomous vehicles as well. It's like, they see an instance of turkeys crossing the street, and they say, okay, we need 10,000 more training examples so we know what to do with turkeys. But that's not always scalable. And so what I would say is a possible solution is, again, another layer on top of it that's saying whether these rules are good to add or not. And I don't know if that would fix the problem. And I'm sure there are people in RL that have good ideas how to learn from this type of experience, but I don't have a good answer, just that it's really hard.
It's all right. Okay, thank you.
Do you want to do some of the questions, Leilani?
Sure. Through the chat. So I think I ended here. So AM7555, you mentioned traffic cones, which have different properties from people, but these properties changed. For example, in extreme weather, more common nowadays, such that traffic cones can suddenly fly across the road. How should AVs cope with this unexpected behavior? Oh my gosh, yes, this is my favorite example. So actually, one of the examples I used in my thesis was this idea of a mailbox crossing the street. And actually, we found that in some hurricanes, in the southern part of the United States, actually, they did see mailboxes floating across the street, which is kind of funny. So how do we deal with that type of unexpected behavior? We synthesize it with different weather information. So just as like I think Alex was saying before, there's always an exception to a rule, and we just have to be prepared for it, right? The difficulty is, when do you put that into your representation? And so a lot of what we've done is we've said, hey, these are strong rules, except in cases, okay, if there's weather, then it might look a little bit different. Or, for example, if you're driving at night, you have a different type of belief system than if you're driving during the day. And of course, we won't be able to handle all of it, right? But that's ended up working pretty well for us for the types of exceptions that we've seen, where again, there are these clearly unreasonable situations where with a little bit more information, it becomes reasonable. But of course, figuring out how to do that in a scalable way is an open question. Okay, I answered.
I think the next one suggested you would skip this, and I think you
Yeah.
can share the link later, or you
Yeah,
might put this, or I can share this if you send it to me, Leilani. Paul Jackson had a question about temporal logic.
Is there any role for temporal logic in phrasing rules? Oh, absolutely. That's an ongoing area we're working on. So again, my colleague Daniel Fremont works on formal verification, and his whole system, Scenic, which I highly recommend, which is a vehicle specification language, is all done in temporal logic. We haven't done it. We haven't done much work on that yet, just because a lot of what we focused on is post hoc analysis for verification. But yeah, you could absolutely do this in a temporal logic as well. You would just need a good translator, which we are still dealing with. You're still open to not a number x over 0 issues, though, aren't you? On the other hand, if this is from Peter. On the other hand, if there was to be an ontology-dependent software engineering approach that might help deliver error-proof software. I mean, that's absolutely right. Like, we're not guaranteed to handle the not a number or x over 0 issue. We would have to observe the behavior first. Right, but we do have some ontologies built into the system. I didn't get a whole lot of time to talk about, and I'm not familiar with this work, but I mean, there are always issues that this won't catch, but the clearly wrong ones it will, and it will also work pretty well as like a pre-checker leading up to what could be an possible accident. Let me see what else I can get through. So Robin asked,
if you're running out of time, Leilani, I mean, you might just pick one at random, and then we can wrap up. Yeah.
Let me see. Oh, someone's quoting Rodney Brooks, so let me take that one, and then I can download the chat and answer some questions.
I can send it over.
Okay, so I believe it was Andrew Ng or Rodney Brooks, I can't really remember, two of my favorite people, who brought up the fact that traffic infrastructure is fine-tuned to the human being, and that if we introduce autonomous vehicles, some fine-tuning should also be expected. Do you agree with that, or do you think we should solve everything from the algorithmic side? Oh, I'm going to have a hot take on this. So I think that, where I live in Santa Cruz, also a plug for Nessie 2025 in beautiful Santa Cruz. We're just 40 minutes from Silicon Valley, about a little more than an hour from San Francisco. But I think one of the things that you see is, especially in San Francisco, they have all these autonomous vehicles on the road, and I'm going to be getting to this question. And I actually think that one of the biggest problems with autonomous vehicles right now, and the fact that they are not behaving as well as we want, besides the type of common sense symbolic reasoning problem I've talked about, which I think is the most important one, I think the second most important one is exactly this, the infrastructure, right? We don't just need, autonomous vehicles to sort of be able to understand human behavior, but we also need them to be confident in these types of in these confidence scenarios. And a lot of that is having like smart traffic lights or vehicle to vehicle communication, or having the roads be on a grid so that we're constantly getting information, or having charging ports so they always have enough power. And so I agree. I mean, I think that the infrastructure is going to have to change immensely if we want to have autonomous vehicles on the road. And I think that's a whole problem that I don't pretend I know about. So I would agree with that.
Yeah, great point, Leilani. I think, yeah, let's wrap up at this point because it's been an hour of your time, but thank you for being so generous. And again, I'll send you the chat transcript in case you feel compelled or tempted to respond, but don't feel obliged to. But thanks for taking time, and we'll upload the video on YouTube shortly and send you the link, Leilani.
Oh, great. Thanks so much. Yeah, it was a lot of fun. Thank you for having me. And
Thanks
for all
for
the
being
great
here.
questions.
Bye.
Bye.